So machine learning is just one of these hot button topics. It's already having a significant impact in both games and film. And it turns out that PDG has a really nice fit with this important upcoming field. And this is because machine learning requires just a ton of data. It needs a lot of processing as well to crunch through all that data as it's doing its training thing. And finally, it needs a lot of trial and error to kind of get it right. And these are all things that PDG just happens to be really, really good at. Let's take a look at how PDG can be applied to machine learning. And we're going to show you this through a couple of examples. But keep in mind that these things are just examples around terrain, okay? They're here so that we can clearly understand the relationship between PDG and machine learning and see it in context, but they're not themselves yet ready for production, okay? So with that in mind, let's take a look at the first example, and this one is around fast terrain erosion, okay? So the idea here is that, we're just gonna take a piece of terrain and we're gonna erode it, right? And we have lots of tools in Houdini to be able to do that. This all works great, except the fact that it just takes a long time to do. And so the idea here is, can we create a machine learning system that, is going to give us, pretty similar results, but and hopefully just do it a lot faster. Okay. So for those of us in the audience who are not familiar with the process of machine learning, I'm just going to quickly lay out the steps for you. So in general, machine learning really, well, you can't learn anything unless you give it lots and lots of examples, right? So the first thing we're going to do is just basically create lots and lots of data, examples of uneroded terrain versus eroded terrain, and kind of show it to the system, and hopefully it learns that. For each of these pairs that we create, we're going to want to flatten it to a pair of images. And this is because our machine learning algorithm happens to be image-based. Okay? On the left, you see the original uneroded height map. And on the right, you see a color image, because after erosion, we actually get a couple more channels. We get the debris and the water fields. And we're using the green and blue channels for those. And that's why that's a color image there. So once the data is ready, what we want to do is we want to create an appropriate machine learning model. And by that, I mean something that's, it's got the right configuration to be really able to capture the information we're showing it, right? And with the model created, we'll run the machine learning training. By that, I mean show this model all the data that we've gathered, so it can learn. And at the end of that, we'll take a look at how the model is doing. Hopefully, it's doing well, but if it's not doing well, then we're going to go back up and we're going to just tweak the model and just keep on doing this over and over again until we get something that is producing good results. And hopefully, at that point, if we show it something it hasn't seen before, it'll make a really good guess and give us good results. Okay. So with that in mind, let's take a look at what this looks like with PDG. So just like Scott has shown you before, PDG is just capable of crunching out tons and tons of variations, but that doesn't really stop with just effects. So here we're going to create lots of different variations of the terrain, different roughness, different offsets, etc., and create all these versions of the terrain that we're going to erode to create pairs like this. So on the left is the uneroded version, and the right is the eroded version. And once again, you see in the coloration because we're using the blue and green channels to represent the debris and water. So next, we're going to go and, like we described, we're going to flatten this. Okay, so on the left, you've got the uneroded height map, which is black and white. On the right, the eroded version with the water and debris. And we're going to montage this together to form these image pairs. And we're going to get lots and lots of those, like so. So at this point, our data set is ready, okay, for machine learning. And now we need to kind of figure out the right model to machine learn with, right? Generally, these days, we have a pretty good intuition on what kind of model to use. But there's no really hard guidelines. And there's just so many different ways you can configure these things. Like how many layers do I use? How many, if I'm doing convolution, what's the filter size? What's the learning rate? So these different configurations in machine learning speak is called hyperparameters. And so because we don't really know what's going to work well, people just end up trying lots of different stuff at the same time. Well, they tried in serial, but now that we have PDG, we can really, instead of doing it one at a time, we can just say, hey, you know what? Let's try all of these things together at the same time. So what we're really doing here is hyperparameter space searching with PDG. Okay, so I'm going to wedge out a couple of different variations here. On top, you see I'm trying 2 different settings on the number of layers. And the third node down, I'm trying different filter sizes and 3 different variations of that. So 2 times 3 is 6 total different variations we're going to try. And then we're going to create the machine learning model and run that machine learning. So this is the only step that actually really requires any kind of machine learning expertise. You need somebody who knows the machine learning stuff to kind of alter the training code a little bit based on the upstream wedge settings, right? But once we do that, we can run all 6 of these things in parallel. And this last step here, we're going to analyze all the results and produce ourselves a little report. OK, so once we've done this, we can take a look at the report. And it looks something like this. You can see the upper left hand here is clearly something that's not doing so well. You can even sense it by the way the kind of lines are just jumping all over the place. And you can intuitively see that on the bottom right-hand corner are things that are just converging a lot better. And indeed, once we take a look at the final results here, and we really see that. The one on the top upper left hand has just got pock marks all over the place, and it's just a mess. Whereas on the bottom right-hand corner, things are looking a lot better. Okay, so once we have this, we're going to kind of just pick out the best one of these, and then and show it something it hasn't seen before. So one of these images here is produced by machine learning. Can you tell which? Turns out the top one is the one created with SOPs, with actual simulation, while the bottom one is the one that machine learning produced. It hasn't. The amazing thing is that it hasn't really seen this at all. It's just a totally new sample, and it just guessed at the result, and you got that. So it looks very, very similar, but the only thing is it's like 50,000 times faster. So it's pretty crazy. And what's also really cool about it is that you can see that it also learned the debris and water fields as well. So you can use this as like a preview. You can use it as a first starting point and just kind of carry on the work from there. So yeah, so crazy speed from machine learning.